like that, you can recognize which finger is closer and which finger is further away. Some of this comes actually from a learning experience. So you can recognize that if you see a finger which is bigger, that you already learned that if you subconsciously almost assume that they are of equal size, so the one which is bigger is closer. So you can, if you close your one eye from the experiences, you can recognize which one is bigger, which one is not. But however, if we are able to have a depth perception even without knowing how big objects are. And all creatures actually which have two eyes directed in the same direction have this capability. There are also creatures which actually have eyes on the side. The evolution actually made them that way because, well, most frequently they were prey. So those animals which have eyes on the side, they can see, their peripheral vision is bigger, so they can almost see what is behind them. So if there was a predator, they were able to spot the predator really quickly. Well, we are predators. I mean, our eyes are made for a creature which is going to hunt. And so what we do is we direct our eyes on the prey, and we can accurately determine what is the distance to the prey, and we can accurately jump on it. Now, how do we do it? It is that because of the location of our eyes, we see two different pictures. And the best way to see it, I mean, why don't you close your eye, one eye, and align two fingers with me. So I and two fingers are in straight line, and then switch the eyes. So open the other eye. You will see that the object shifted. That the picture. This way, you recognize that the two eyes see two different pictures. Now, most of the time, well, and the rest is how the brain functions. So for example, if I focus on Kyle, fact that I see two atoms doesn't matter, but I see two atoms. If I focus both eyes on Kyle, I see two atoms. I will try to do it. So look at one object and notice. I mean, you will do it almost subconsciously, that you will have to concentrate to observe other detail in the picture which is really split. All right. Probably you saw, more about this, Mike. Probably you saw, how many of you played with this, and how many of you failed actually to see it three-dimensionally? Ian, you failed or you saw it? I mean, did you play? Did you play with this? All right. Well, let's hope that this time you will see it. And so I will show you how to do this. And actually, how about if I also show it on the screen. Actually, you can do it even on the screen. So if you have a good eye, I mean, if you already learn how to do it, you would be able to see it on the screen as well. Well, so what I suggest now, I mean, how to do it, and it doesn't matter which one you start with, because now you will be suppressing your instinct. Our instinct is that if we focus our eye on a particular detail, it is that we also direct the axis, principal axis of our eye in such a way that they cross each other at that point. So the principal axes are actually not parallel, but they intersect at the point at which we focus our eye. So actually this plane where the two axes intersect is the plane of our focus. From that, the lens of our eye makes clear image on retina from this plane. Now we are going to cheat our brain. And, well, we can do it this way. Bring that page very close to your face in such a way that actually you touch the page with your nose. And find a certain spot. I mean, this way, actually, it is that you will see a lot of spots. So align one of those spots so that you see one. You won't be able to focus on it, obviously, because the distance is closer than your point of your eye. However, that spot which you see, and it will be blurry, is an image formed by looking at two different spots on the picture. You won't look at the same spot. Well, anyway, then put that spot just in front of you, and very slowly, so that you look staring at that single spot, move the picture further and further and further away until it's in focus. And then, boom, you see it in 3 dimensions. Can you try it? So go ahead and play with this. If you succeed getting it, well, pass that page to another person. Now let me try actually to get it 3-dimensional from there. Okay, I already got it. Anybody got it already 3-dimensionally? Okay. Well, just to test you, Adam, that you see it right. So, which Saturns are closer to you, the 4 on the right-hand side or the 4 on the left-hand side? I mean, let's say the Saturns in the well, these are Saturns, right? I mean, in the middle row. Because the other one, I think, is Neptune. It also has a ring, but it's much fainter ring than Saturn. So, Adam? Andrew, how about you? Then you see that... I wonder if you crossed your eyes, because actually we can do it in many ways. Important thing is that you look with one eye on one and with the other one on the other. Actually, you can see over here also. It is. I mean, the fact that we see those 2 different images when I align the fingers is called a parallaxis. And actually, compare these two, right? So here we have such a relative orientation, and it is changing. Now, what you are doing on this, I mean, physics about this, how we see it 3-dimensionally. If you look, for example, with one eye on this one and with the other eye on this one. Well, principal axis actually pass through these points over here, and from these 2 planets, images of planets, we create the image. So we think that this is one object, and then if we concentrate on this one, we see 2 of those. If we focus on this one, we see 2 of those. But whenever we focus on one, we will see how deep it is because of this parallaxis. You may try also to do it on the other picture. because with this picture, you will see that these objects are also tilted. It's not that easy on this screen. I try here. All right, so how do you see tilted? Let's say well, let's say that the second from the bottom row, the row second from the bottom. So how the two shapes on the left-hand side are tilted? This way or that way? Andrew, can you see it?
Yeah, I'm not sure which way you're oriented. As far as the page,
yeah, the way you look at this. On the, yeah, so on your left-hand side.
The furthest left one looks, those parts partly off the page look straight up and down, and the next one is tilted sort of into the page.
Right. And the next one?
Back straight.
Actually, according to me, it's already that way, but that's fine.
Yeah.
All right, Ian, have you succeeded seeing it or not yet? Not yet? Well, we will do it. I'll show you how to do it after the class. Now, when I was a kid, actually, I knew about, because I learned about this. This is, we call it this three-dimensional vision as stereoscopic vision. And I knew, I don't know where I learned that, but I read somewhere. And there was, I started then to apply it to a different game. I don't know how many, well, probably everybody has played with something which is called, you're supposed to find a difference in pictures. And actually, this is very unnatural trick which I'm doing, which I'll show you now. But you can train your eyes to look independently on various objects, and then actually, if there is a difference, it is easy to spot. So actually, I'm going to look at two objects now. Well, because if you look at this. I'm going to look at this like a chameleon. So with left eye, I'm going to look at the left picture, and with the right eye, I'm going to look at the right picture, and see the differences practically immediately, because I will, if you train your eye to see that, it's actually when you're home, why don't you try it? So let me. Okay, I'm still fighting with focusing my eye.
Not too bad on the big screen version.
All right, I got it. Yeah. So now I see here, here. Oh yeah. Right. Now, actually, I had even to diverge my axis because. But because I was doing it since I was a kid, I was able to do it. And actually what I see it is that like over here, this one. My brain switches back and forth from red to yellow. So those objects which are different, they blink, and that way I see the difference. Actually, I can't. Oh, how about let's take a look at this one. Now that screen is too big actually for me. I'm not sure, because before what I have to do is I have to look at. Oh, I got it. I have to look at the picture in such a way that I see 3 clear pictures rather than 4. Yes. So now let's see if I can. Yeah. So this. Oh, it doesn't blink. So I see that this leaf over here. I see that the bees are different. Now there's something wrong with the eyes. Oh, there's a difference over here, and the flower over here, oh, and the print. All right. So have fun with this, with both looking at 3-dimensional images and trying to find difference, but by looking at the independently with your eyes and creating separate picture. Now, those people actually who cannot see 3-dimensionally, I mean, because there are people who develop one eye only, and they look only with one eye. So one eye is very weak, and the brain actually switches off that eye. Actually, one of the students, but probably you can see one of the physics students walking around. He covers one eye with a patch, and actually what he is doing is not that his eye is, he covers the healthy eye. And the reason for it is that, well, the treatment is that he is forced now to look with the other eye, which the brain is trying to turn off. So he covers the healthy eye in order to develop better the eye which is getting weaker and weaker. All right. Now I would like to talk to to come back to the wave nature of light and electromagnetic radiation.
How do you know which one of your eyes is strong?
A physician will actually to determine, but you could see it too. Each of us actually has one eye stronger and one eye weaker. And, well, you can recognize it by just closing one eye and see how sharp you see the world, and then close the other eye and see how sharp you see the other eye. And brain actually automatically turns off the weaker eye. So, oh, and why don't you take off your glasses and make this experiment? Look at me with one eye and with the other eye. Well, most likely with one of the eyes you can focus better than with the other eye. Do you see that? Right. So the brain actually condemns the weaker eye, and as time passes by, it will be shutting it off more and more and more. All right. I mean, the question was how we recognize which eye is stronger and which eye is being suppressed by the brain. Now, because I said when we started to talk about electromagnetic radiation or with radiation in general, that it manifests actually both properties. Sometimes it behaves like a beam of particles, which you could think about it as it's a stream of bullet flying through space, and sometimes it behaves like a wave passing through the medium. And actually, if you study modern physics, you could recognize that that objects which we in the past recognized as particles, like electrons, for example, under certain circumstances will behave also like waves. So duality, this wave-particle duality, does not concern only electromagnetic waves like light, but also beams of protons, beams of electrons, beams of small objects. Probably, I mean, in principle, actually, if there was a creature which was observing us, and that creature would recognize us as particles, they maybe can even discover wave nature of all of us. Now, for quantum mechanics is actually the discipline of physics which studies de Broglie, a French scientist, French physicist who started quantum mechanics practically, came with an idea that a beam of particles can also be considered as a wave. And there are links between the description of certain beam as beam of particles and describing it also as a wave. So if it is a beam of particles, then we associate with the beam of particles energy of a single particle and momentum of a single particle. If we consider the same phenomenon as a wave, then we would refer to frequency with which it oscillates and also the wavelength. Now, things which wave can do and particles can't, there are two things. One is interference. And interference is a phenomenon that results from passing two or more waves through a single spot. And if the waves passes through the same spot, if the two waves, well, we say that they are coherent, which means that they oscillate in the same way, that at this point the two waves can reinforce the oscillations, or they can neutralize their oscillations. So if I think about a wave or two waves passing through this point, and if it happens that the two waves meet in such a way that crest meets crest and trough meets trough, then the oscillations will double. However, if it happens that crest from one wave meets trough of the other wave, then the two oscillations will cancel each other out, and there will be no oscillations at all. Maybe for tomorrow I will bring a mechanical model of a wave, so that we can see it. So interference is one of the phenomena which is associated with wave character of certain beam. If we were thinking about it in a particle-like wave, so a particle-like model, it would mean that if we throw two stones toward one point, and when the two stones meet, they can actually create either single huge stone, or they could disappear completely. This is what interference means. The second phenomenon, which is also wave nature, which exhibits wave nature, is called diffraction. And diffraction is bending of a wave around objects. Well, I am sending waves now. And so sound is actually a wave. And because it is a wave, it undergoes diffraction. And therefore, if I hide behind the screen, you still can hear me. I cannot throw objects from behind toward you. Because if I throw an object, it will not be able to go around the obstacle. All right. So now I will make a digression, and in order to actually see effects on the interference and diffraction, I want to come back to the energy carried by electromagnetic waves. So let's say that this is a plot of the electric field of a wave which travels to the right. And when it travels, it carries energy. And really, how strong is that electromagnetic radiation is dependent on this, how much energy is approaching us. So if we see that an object is brighter, it means actually that it sends more energy toward our retina. If it is dimmer, then it doesn't. All right, so by U of t, we designed, we associated symbol U with an energy density. So right now I'm going to, let's say that at a particular instant, I freeze the wave. Let's say that this is a plot of electric field vector. So at this instant, electric field vector is, at that location, electric field is up. Over here, it's 0, and over here, it's down. Now, what carries energy in an electromagnetic wave? Well, electromagnetic wave consists of two fields, electric field and magnetic field. And when we were talking about electric field, you remember that we were talking about energy density associated with electric field. When we were talking about magnetic field, we were talking about energy density associated with the magnetic field. Now we will have to use them both together. I bet that you don't remember the formulas, but probably you will recall that density of electric field was proportional to the square of the electric field vector. Density of magnetic field was proportional to the square of magnetic field vector, and with a certain proportionality coefficient. 1/2 multiplied by permittivity of free space was for electric field, and 1/2 divided by permeability of free space was for magnetic field. Additionally, in an electromagnetic wave, we recognize, we have already found a relationship between electric and magnetic field, and it's fixed. The quotient of electric field over magnetic field is always equal to speed of light. So I can actually relate energy density to just one of the fields, and it doesn't matter which one. Traditionally, we pick electric field vector, so we associate it with electric field. So instead of having magnetic field vector, I put quotient of electric field vector divided by magnitude of electric field vector divided by speed of light. And if I simplify it, I get that energy density at a particular location is equal to permittivity of free space multiplied by square of the electric field vector. In other words, square of the electric field strength. So if we froze the wave, because this plot is at a particular instant, we could recognize that at this point energy density is 0. Now let's find points where the electric where the energy density has the highest value. So how about here? Say yes or no. Yes, correct. Now how about here? Yes. Fact that that electric field vector, the component of electric field, vertical component of electric field vector is negative, doesn't matter because we have to square that. So here we have a certain distribution of energy density. Well, actually, if we look at light, how far is from crest to crest? What is? I mean, if we're looking at the light coming out from the projector, what is approximately this distance? Or what is the order of it? Is it 1 meter? No. More or less? Less. Let's say 1 millimeter. Less. 1 micron. Less, right? For green light, the distance, for monochromatic green light, the distance from crest to crest is half a micron. Precisely, it is 0.55 microns. Well, so, and from this point to this point, it is 1/4 of a micron. Now, this entire shape is traveling toward with speed of light. Well, so you can recognize that there will be huge number of those crests and troughs which will approach us, so that energy pulses, because actually if we look at this, the energy is not distributed uniformly through space, but in kind of pulses. We have one pulse over here, another pulse over here, another pulse over there, but they are coming to us with such a frequency that we don't care actually what is the intensity at a particular pulse and between them. For us, the effect is average. Therefore, rather than looking at the energy density, let's take a look at the average energy density. Here's a plot of energy density, and we can recognize that average energy density will be somewhere around here. I mean, this is symmetrical. Right? So this is going to be the average energy density associated with the electromagnetic wave. And so I can recognize that it will be half of whatever we had at maximum. Let's say if I calculate energy density, let's say at this point, I will get energy density corresponding to the this electric field strength. And let's say that this is the value. Average density will have half of that value. Now, since this is, for a sinusoidal wave, I can recognize that if I divide peak value by square root of 2, I will get root mean square value of electric field. So I can write down that average density is just permittivity of free space multiplied by square of root mean square value of the electric field strength. Now, if I did this with using magnetic field, then I would get an expression which is equivalent. And actually, you can do it either by substituting electric field, root mean square value of electric field here by product of speed of light and root mean square value of magnetic field strength, or you could do it over there. Now, how? Well, because electromagnetic wave always travels in the direction which is perpendicular to electric field vector and magnetic field vector, well, a guy whose name was Poynting recognized that we can take those two electric fields to indicate in which direction energy is carried. And, well, he associated with the motion of the wave. So if electric field oscillates vertically, a magnetic field oscillates horizontally. Now let's say that at the instant when electric field is up, magnetic field is this way. Using right-hand rule, I mean, sometimes in the past we have already done it. We determined that the wave associated with these two fields is going to travel to the right. If at the same time, if it happened that at the same time electric field was this way and magnetic field were that way, then it would correspond to a wave traveling to your left. So the direction of which way a wave travels is associated with the direction of those two vectors, electric and magnetic field, and the vector product of those two indicates with the which way, because it follows right-hand rule. So vector product also follows right-hand rule. So vector product will indicate the direction of motion of a wave. Well, it happens also that when we calculate magnitude of vector product, we have magnitude of electric field and magnitude of magnetic field. And since electric and magnetic field are also proportional to each other, then this vector, the magnitude of vector product is going to be proportional to square of the electric field strength or square of magnetic field strength. So somehow this vector product also indicates how much energy is carried by a wave. So this vector product says, I mean, this vector, which we referred as Poynting vector, and it's know that this is y over here, so it does not point at anything. It's coincidence that it sounds like it is pointing somewhere. Now, this vector, referred as Poynting vector, says simultaneously at what rate the energy flows and in which direction. All right, so we have already discussed the direction, that if electric field is this way and magnetic field is this way, then the wave is going to travel to the right. Now let's see at the energy carried by the wave. So let's say that I will take a certain surface which is perpendicular to the direction of propagation of the wave. And here I have the wave, which passes and travels to the right. And I will evaluate how much energy, I will compare actually this energy to the magnitude of the Poynting vector. So here I start with with calculations of the magnitude of the Poynting vector. So I will have 1 over permeability of free space, then magnitude of the first vector times magnitude of the second vector times sine of the angle between them. Angle between them is 90 degrees. Sine of 90 degrees is 1. So this will be the expression which we'll get by calculating magnitude of this vector product. And I can now replace strength of one field with the strength of the other field. And doesn't matter which way I do it. Traditionally, we use more frequently electric fields, probably because it's C times bigger number than magnetic field strength, although we can change units in such a way that they are all reasonable numbers. All right, now I just simplified this expression. I recognize that speed of light is 1 over square root of permittivity and of product of permittivity and permeability. The next step is also just a mathematical step. Yes, so I simplified. Well, I got rid of mu 0 from square root of mu 0 from numerator and the denominator. I added 1 square root of permittivity of free space in the numerator, then in the denominator. So in the numerator, I will have permittivity of free space, and here I have 1 over square root, and this 1 over square root gives me speed of light. and permittivity of free space multiplied by square of electric field strength give me energy density at this particular point. So I have that the magnitude of the Poynting vector really says that it is speed of light multiplied by energy density. All right, so let's consider this point over here. I mean, let's see how much energy is going to cross this surface in time dt. Well, whatever, I mean, it's again the same type of a calculation when we're thinking about crossing the wall over here. So the volume which, I mean, the volume of that wave which will cross this surface is going to be equal to speed of light multiplied by the considered time. So whatever wave is now in this volume, it is a part of the wave which crossed that left-hand side surface. All right, let's calculate how much energy crossed this surface or related to something. So I will have to take this volume and multiply by the energy density of the wave within this volume. Now you have recognized that thickness of this volume is differential. So although on the picture it looks like the electric field varies significantly, but in a differential volume it does not. So what I have to do over here is just put energy density within the volume. Therefore, I mean, I can now substitute this energy density over here by amount of energy crossing this surface divided by the area of this surface and divided by the time. So what magnitude of the Poynting vector represents is amount of energy crossing the surface divided by area of that surface and the time, right? So it says how much energy. Magnitude of Poynting vector says, therefore, how much energy I mean, really, I mean, probably the best way to phrase it would be that this is rate at which energy is being transferred through the surface per unit area of that surface. Why don't you repeat this phrase to your neighbor? That the magnitude of the Poynting vector represents the rate at which energy is being transferred through a unit area of a surface perpendicular to that wave. Say it. You can also say, rather than saying rate, you can say that this is amount of energy which is passing through a surface in a unit time. All right. I will just introduce this one more quantity and stop the lecture over here. Now the average value, the average value of that quantity is referred in physics as intensity of the radiation. So now let's combine the previous phrase by a phrase average value of it to get the definition of intensity. Can somebody do that? I want you really to comprehend concept of intensity. What is intensity? All right, so let's say intensity of light on this surface. Adam, you are willing to say it? Okay, let's try it.
It's the average rate at which energy is, or from which electromagnetic wave is transferring energy to that imaginary surface.
Incomplete?
Surface.
Per?
Per.
Yes, Lee? What did he miss? No, he said rate, so this is fine. Per unit area, correct. All right. So how about if we think about it this way? Let's say that intensity over here is 1 watt per meter square. Okay. How much energy is going? How much electromagnetic energy will fall? And for simplicity, let's say that all the energy which falls on the surface is absorbed. How much energy this object is going to absorb in 1 second, 2 seconds? What would we have to do? Yeah, so Andrew will answer that. So we need, correct, we will need the area of this surface, right?
So we take that energy density, what was it, 1 watt per meter?
It's not energy density, I said intensity. Yes, so we take intensity, 1 watt, right, multiply by the area. Okay, let's say that this is 1/4 of a meter square. It's reasonable. Yes, so we will have 1/4 of a meter square multiplied by 1 watt, and then by 2 seconds. And this way, we will get what? We don't say average. Say energy. Okay, which energy? Absorbed by this surface. Correct. All right. So this will be all. We can also recognize that intensity is associated with average density. We will have to multiply average density of the wave by speed of light, and we will get intensity. So this will be all for today. Thank you very much, and see you tomorrow.